Hello everyone, I'm Stefan Tabernig, and today I'd like to talk about carrier collection in optically resonant nanostructures for quantum dot solar cells. To begin with, I'd like to highlight and thank my group in the Netherlands at AMOLF, which is the Photonic Materials Group under supervision of Albert Polman, as well as the group I'm visiting at the moment, which is the Colloidal Quantum Dot Group under supervision of Shujian Huang at UNSW in Sydney. So what we're working with here is basically a quantum dot solar cell, which uses quantum dot solids as the absorber material. These basically look like the TM image that you can see here, and if you zoom in more, you can see the individual components, which are basically, in this case, lead sulfide nanocrystals surrounded by ligands as spacers. So those solids make up the absorber layer in the quantum dot solar cell. In this case, you see gold as the back contact, zinc oxide as the n-type layer, and ITA on top. Those systems come with a couple of advantages. First of all, having already decent efficiencies. Moreover, allowing you to tune the band gap, which makes it interesting for multi-junction solar cell applications. Then the quantum dots themselves are solution processable, and due to the fact that those cells are really thin, you can use them for applications that require material flexibility. There's some disadvantages, which are an intrinsic VOC loss that's associated with those quantum dot solids, the fact that they're expensive to make, and due to the lead are also a little bit toxic, as well as the low carrier diffusion length that is associated with those quantum dot solids. Now, what I highlighted here in bold is basically something we would like to address with the design we propose, and those issues can all be addressed by basically using less absorber volume in the quantum dot solar cell. What we aim for is to achieve this reduction of required absorber material by making the absorber layer itself resonant with light. Now, that would give you the structure you can see on the right, where you basically have quantum dot cylinders embedded in zinc oxide on some residual quantum dots at the bottom, and their dimensions will be chosen such that they maximize the absorption per unit volume in the absorber layer. This then will provide you with the benefits of having less material, so it will be cheaper, less toxic, and in this whole geometry you also don't need to introduce any new materials. And we warrant this new design by basically saying that this redesigned optical structure will basically enhance absorption per unit volume and ideally also improve the electric performance later on. You get to this design of your cylinders arranged periodically and with the respective dimensions by starting with looking at the optical properties of your quantum dots. What you see here is the complex refractive index. On the top you see the real, and on the bottom you see the imaginary part. And if you look closely, you can see that depending on which ligands you use, like oleic acid or lead iodide, and which band gaps you use, those properties can change quite significantly. In our case, we use the band gap of 1.32 eV and lead iodide ligands, which are fairly standard ligands to use for quantum dots in a solar cell. Then you go on and put those optical constants into your simulation software. In our case, we used numerical FDTD, which allows you to do optical simulations. And you start off by just making your cylinder of quantum dots and looking at, for example, the scattering efficiency of that. And then you slowly introduce more and more realistic surroundings, like the zinc oxide around it or this thin residual layer, and look at how the optical properties change. And you go on and on and on until you obtain your final structure, where you can see that we here introduce the periodicity as well. And instead of looking at the scattering efficiency, we now look at the absorption as a function of wavelength. Here we've done this to compare a flat cell with patterned one, flat in blue, patterned in yellow. And this comparison was done for cells that use the same amount of absorber volume. But even though they do that, they show quite different absorption spectra, as you can see here. And more interestingly, the patterned one absorbs light much better over all of the investigated wavelength range. And the relative comparison can be seen here in gray, where you see that basically towards the band gap you absorb more and more and more compared to a flat solar cell. That was it for the optics. We also would like to know what we get electronically from such a structure, and for this we did simulations on the charge transport by solving drift diffusion equations. Again, we used a program that solves this numerically, in this case numerical charge. And to do this we looked into literature for reference values as well as our experimental data, and basically tried to calibrate our simulations such that they fit what we get in experiments. In this case, you can see it here as for the solar cell efficiency as a function of absorber layer thickness. And just for your reference, what you see here on the right is basically the band diagram of the quantum dot solar cell. And you see that you have bending across most of the active layer, which makes sense for this kind of solar cell as it's a depleted heterojunction solar cell, meaning that your depletion region covers a considerable range of your absorber material. The electronic simulations provide you with a range of interesting quantities to look at. One of them is the electric field across the cell, where basically this color gradient tells you the direction, but also the strength of the electric field. So the closer yellow and red are, for example, the stronger the electric field in that region. Now, for the pattern cell, that already looks really interesting, where you see that the gradient is much stronger and kind of curves into the cylinder a little bit here. And this becomes even more interesting if you look at this in connection with the generation profile. Again, first for the planar case, where you see that it's kind of trivial, so most of the generation happens all the way in the front, and it becomes less the deeper you go in your cell. But the pattern case looks much more interesting. Instead of having most of the generation also happening in the front, most of it happens either in the center, but even more all the way at the back of the cylinder. And this is basically just a result of summing over multiple resonances across the full wavelength range of interest that you have, optical resonances that you have in your cylinder. And what this basically leads to is that most of your carriers are generated here, and if you now think of those electrons and holes individually, starting with the holes, the hole only has to go all the way down here to reach the gold contact, and the electrons in principle would have to go all the way up here to reach the ITO. But due to the fact that mobilities in zinc oxide are much better than in the quantum dot solid, just getting here would already be really good for extraction. And that's basically where the electric fields come into play, because if you look at the direction, then you can see that the electric fields will basically aid the electron in getting to the interface so that it can be extracted much sooner than you would have in the planar case, for example. Now, conceptually this looks interesting. Does this mean that we've improved solar cell performance? To find out about that, it makes sense to look at IV curves that we simulated. Now here you see the comparison between the pattern cell in purple with two reference cells. One, the red one, corresponding to a planar one with 180 nanometers active layer. This one basically uses the same amount of absorber volume. And the other comparison is comparing the patterned one to a 400 nanometer active layer planar one, which basically has the same stack height as our pattern cell. And if you look at the numbers for that, then you will find that the pattern cell seems to combine the high JSC that you would expect from a thick planar one with a high VOC that you get from a thin planar one. Now, unfortunately, you suffer a little bit in fill factor, which in the end makes you reach a similar efficiency in the pattern case as you would have in the thin planar case. But in any case, to us, this was promising and interesting enough to warrant going into fabrication and experiment to find out if we can fabricate the structure, and maybe also find out how big of an issue the fill factor here is. So what you can see here is basically the fabrication of this patterned PN junction, starting by spin coating zinc oxide nanoparticles onto our substrate, and then pushing a PDMS stamp into them. And after this whole arrangement has cured, you can infiltrate it with quantum dot solution. That's what you can see indicated here. And after this, you can just finalize your cell with the gold evaporation at the back, and you will end up with such a structure where you can see here the patterned zinc oxide, and here the quantum dot absorber that was basically poured onto it afterwards. Now, we already have some preliminary results that I'd like to show you. What you see here is basically the comparison between the patterned cell and the planar one. And you see that while they have quite similar short circuit currents, the shape of their EQE spectra is quite different. The patterned one is much smoother across most of the spectrum, whereas the planar one shows you, beside the first exciton peak, 3 additional peaks which correspond to Fabry-Perot resonances. To conclude, I hope that I could convince you of our approach of basically reshaping the absorber material and therefore needing less of it, how a structure that evolves from this can aid you with charge carrier extraction, and that we've already found a good and easy way to fabricate the structures. With this, I'd like to thank you for your attention and hope that I can show you more interesting electronic data on this in the near future.